Now it's time. Okay. Okay. So the second speaker of this afternoon is by Professor Yinqi Zheng from Peking University. So he will speak about power-based Hall symmetry for Lagrangian fibrillation. Okay, please.
Thank you. Thank you very much for the invitation. It's my pleasure to speak here. So today I'd like to talk about a curious symmetry we discovered for Lagrangian fibrations and the various ways to explain it. And this is all joint work with Junliang Shen. So the starting point of the story is we're interested in two things and we want to relate them. The first is the topology of a Lagrangian fibration. And the second thing is the Hodge theory of symplectic varieties. And here by symplectic, I mean and the holomorphic sense. So I want to relate the two sides, one topological side, the other Hodge theoretic side. And first of all, the definitions. So everything will be over the complex numbers, and my variety M will be a non-singular variety, and it's called symplectic if there's a closed non-degenerate symplectic form. And then, so this is definition being symplectic, and then a fibration. In my talk, it will always be a projective fibration, and the base will always be normal, and it's called Lagrangian if the holomorphic two form restricted to the smooth locus of the fibers is zero. So this is just the definition. And now, when we think about the Lagrangian fibrations, we usually think about two sets of examples. And there's the compact ones and the non-compact ones. So for the compact ones, so there are maybe two compact examples. The first is the two-dimensional case, which is an elliptic K3 surface or any elliptic symplectic surface. And then the higher dimensional examples are given usually when you have a K3 surface, you can consider, say, the moduli of one-dimensional sheaves on the K3. So this is the moduli of one-dimensional sheaves. And then you have this map from the moduli space of sheaves to the linear system. And then if you're lucky, the moduli space is smooth, then you get a smooth, compact, hyperkiller variety. And this map will be Lagrangian. And this is the so-called Deauville-Mukai system. And then there's the non-compact example. And the most famous one is the so-called Hitchin system. And this time, this M will be the moduli of Higgs bundles. So this is the moduli of Higgs bundles. And more precisely, so this is the moduli of Higgs bundles on the curve. C, and it means that a Higgs bundle is the vector bundle of E together with a so-called Higgs field. And this Higgs field is an element in the so it's a one form with coefficients in the anamorphism of E. So this is a one form. And there's some general facts about Lagrangian fibrations. For example, since we start with a symplectic variety, it will be the dimension will be even, and then the dimension of the base and the dimension of the fibers will be half of the dimension of the total space, and the general fibers of the fibration will be abelian varieties. So there's a couple of general facts, and so now to talk about the topology of the fibration pi, we need a certain machinery to encode topological information. And one way to encode enough information is to consider the derived push forward of say the constant sheaf of M. And then the machinery we use will be the BVD or BVDG decomposition theorem. It says here that if you push forward the constant sheaf, then you can decompose the derived push forward into the so-called number of so-called perverse sheaves. So roughly, in our case, if M is 2 n-dimensional and B is n-dimensional, the decomposition takes the following form. So I'm writing down a way to remember all the terms. And I'm deliberately messing up a lot of the shifts and the indices. But just to give you an idea how many terms there will be. So there will be 2n plus 1 terms labeled by P0 to P2n. And all these PIs are perverse sheaves up to a shift. So the decomposition happens in the constructible category of the base B. Maybe I should say that as all the decomposition theorems, so this decomposition is not canonical. So this is not canonical. And what really is canonical is a filtration associated with derived push forward, namely that if you consider P0 and P0 together with the second term and together with the third term, and it goes on, and this filtration is canonical. So this is the decomposition theorem, and from this theorem, you just recover all these perverse sheaves, and then immediately you can consider some discrete invariants, some numerical invariants, which is just you take the cohomology of these perverse sheaves and consider, you take the dimension of the cohomology groups. So I call the Pij of pi, so this is my invariant. This will be the dimension of Hj, so the J index, and the I index is for the perverse sheaf pi. So this is what I call the perverse numbers of the map pi. So one has to remember that these are topological numbers, and this concerns the topology of this vibration pi. So that it's naturally associated with the map pi. So this is the topological side. Of course, then there's the Hodge side and the nice numerical invariants that we should remember is usually the Hodge numbers. And here's the prototype for the so-called perverse Hodge symmetry. And it's firstly stated in the compact case. And this is the theorem from maybe 3 years ago with Junliang. We proved that if you start with the Lagrangian vibration, but also you assume that you're in the compact world, meaning that M is a compact but also irreducible symplectic variety. In other words, it's a compact hyperkähler manifold. Then this natural, this interesting symmetry, or it's actually an identity of the numbers. So on the one hand, you have the perverse numbers, which remembers the topology of the map pi. So these are the perverse numbers, and they just equal the Hodge numbers of the source variety n. So you have perverse numbers equal Hodge numbers, and they're totally different things. One side is topological and involves a map, and the other side, of course, is Hodge theoretic, but it doesn't involve the map pi. So there's this symmetry. And we became interested in this because we were aiming at some interesting consequences of the symmetry. First of all, you can use this to give a short proof of a result of Matsushita, namely that if you consider the base B, you can compute its cohomology, and the cohomology will be the same as the cohomology of the projective space. So if M is 2 n-dimensional and B is n-dimensional, then the cohomology B is the same as the cohomology of the projective space Pn. And this result does not use any assumption on B, except that it's normal. Of course, there's this famous result, Professor Huang saying that if you know that B is smooth, then the B is the projective space Pn. And to see this, it's really easy because you just take I equals 0, then what you know is this Pi or P0 is just the constant G. And this is when your B is normal, then you can derive that. Then you see immediately that you can translate these perverse numbers into the Hodge numbers, and the Hodge numbers are given by the H0Js, and those are given by 1, 0, 1, 0. It's the sort of the boundary of the Hodge diamond, and that's how you obtain this result. And also you can also take J equals 0. Then what you recover is the space of invariant cycles. So you can take the cohomology of your M and then restrict to, say, a generic fiber, which is an abelian variety. And then you can consider the space of invariant cycles. And then the answer is, even if the total space may have a lot of cohomology classes, the invariant cycles are only one-dimensional in each even degree. It is generated by the class of relatively ample line bundle. In degree 2, it was a result of Guizhou and Matsushita, and here you can easily generalize it to all degrees. And this is again taking J equals 0, and then again you land in on the Hodge side, you land in the boundary of the Hodge diamond, which is again 1, 0, 1, 0.
So question, so do you have any result on integral coefficient?
Sadly, no. So this, yeah, we can only do rationals.
Okay.
Yeah. So yeah, the whole thing needs many statements involving, say, hard Lefschetz type statements, and we cannot do integral coefficients.
So is this only for even degree cohomology?
So in odd degree cohomology, there's no invariant cycle.
Okay.
Yeah, so it only appears in even degree, and it's one-dimensional in each even degree. It's just because if you take J equals 0, all the HI zeros of your M is 1, 0, 1, 0, goes on. And the PI zeros are precisely the invariant cycles. So let me briefly mention how we prove that. The proof is actually very simple. So there are basically 3 ingredients, and you can see what we use. The first ingredient is it's mostly general. So it says that you can take an ample line bundle or an ample divisor from the base, and you pull it back to M, you do cut product with this pullback of an ample class, and the general theory says that it will induce the perverse filtration on the cohomology of M. So this is how you get how you obtain say the perverse side of the story. This is mostly general. This is I think it's due to De Catado and Miorini. So the only condition we need is the compactness of them. We have to assume M compact to derive this. And the second ingredient is now you have this holomorphic 2 form on your compact hyperkähler. And then the second thing says that doing cut product with the holomorphic 2 form, it actually induces the Hodge filtration. So this is, again, a nilpotent operator. It will induce a filtration, and it is precisely up to some shift of the Hodge filtration on the cohomology of M. So, but I want to emphasize that this result is not, it's not completely general. It has to be, so M has to be compact and also hyperkiller. So this is first, this is the result of Verbitsky. And the key is that it has to use hyperkiller metric. So this is this result is proved by using the hyperkiller metric, and you have to represent the cohomology by harmonic forms, and you do some manipulations with the harmonic forms to arrive at this. So this result highly dependent on the hyperkiller metric. And then the third ingredient is that you have beta, which controls the reverse filtration, the sigma, which controls the Hodge filtration, and then there's a way to deform beta from beta to sigma, and the precise way of deforming it is to deform inside a semi-simple Lie algebra, and it has a name called the LLV algebra. And once you do that, you arrive at the proof, because then the weight spaces will be the dimensions of the weight spaces will be constant. And let me just say a few things about the Lie algebra. So this is the Loinha-Luntz-Verbitsky Lie algebra, and the definition is like this. To take M to be a compact hyperkiller variety, or actually the definition makes sense for any non-singular projective variety. And this Lie algebra is defined to be generated by all hard Lefschetz triples. So you have, say, you take an element in H2 of your M, and you consider whether this element satisfies hard Lefschetz. For example, an ample divisor ample class satisfies hard Lefschetz, then you put it in. If there's some maybe transcendental class that satisfies hard Lefschetz, you also put it in. Then you get a Lie algebra generated by all these SL2 triples. And of course, you can do it with, say, Q coefficients, R coefficients, or C coefficients. And the definition makes sense for all non-singular projective variety. It is only when you have a hyperkiller variety that you can precisely describe what this Lie algebra is, and this is a result of Loinha-Luntz and Verbitsky independently. They say that the algebra it's not some random algebra, it's just the special orthogonal Lie algebra. With complex coefficients, this is the SO of second Betti number plus 2, and with real coefficients, you arrive at the index signature. And with Q coefficients, you arrive at the SO of, so this is the Beauville-Bogomolov Fujiki form, and it's a direct sum of this form together with the rank 2 lattice, 0, -1, -1, 0. And this is the Q form of this Lie algebra. And you can find lots of interesting elements inside this Lie algebra. For example, as I already mentioned, this beta and sigma are both inside this Lie algebra. And also there's the result of Sodak-Tenkov and Green, Kim, Lazar, and Robles, which says that if you consider hyperkiller manifolds and consider its monodromy, or actually the log monodromy, then the log monodromy also lives inside this Lie algebra, meaning that the log monodromy acts via this action of the Lie algebra on the entire cohomology. So this algebra is key to many recent results on the cohomology of hyperkiller varieties or hyperkiller manifolds. And this is how we is also how we prove the perverse Hodge identity in the previous slide. So this is one side of the story, and the interesting thing is that recently we worked a bit on the singular analogs of the, say, the LLV algebra. There we find, of course, then we don't have hyperkiller metrics anymore. We only have a singular symplectic variety. Then, but we had an interesting remark, which is that so this perverse Pij equals Hij, it's just a numerical identity. You may say that it carries a lot less information than, say, the Lie algebra or the hyperkilometric and all that. But actually, if you're willing to assume the identity Pij equals Hij, and then you can argue with some standard results, hard Lefschetz type results, and with also with a bit of help of monodromy, then you can say that you can show that this Pij equals Hij will also imply that cup product with sigma induces the Hodge filtration. So if you assume perverse equals Hodge, you can also prove that cup product with sigma induces the Hodge filtration without any hyperkilometric at all. And this is one result. And if you continue this line of the argument, then again, by applying Green, Kim, Lazen, Robles, you can further show that the log monodromy also sits inside this Lie algebra that you define, and eventually you'll be able to reprove the LLV theorem. So the upshot is, if you start with the Lagrangian fibration, and if you're able to show Pij equals Hij, then you will be able to reprove the LLV theorem without any hyperkilometric at all. Now, further, if you're willing to assume the so-called hyperkiller SYZ conjecture, roughly speaking, it means that all the hyperkiller manifolds can be deformed to a Lagrangian hyperkiller manifold, then this perverse Hodge symmetry plus hyperkiller SYZ will give you a new proof of the LLV theorem without the metric at all. So what you need is only the symmetry and a bit of information from monodromy. And this is a byproduct of the global Torelli theorem, but now it is not purely algebraic proof by Baker and Lane. So this part is metric free, and then the rest of the thing, the argument is to find a way to approach the perverse equals Hodge identity. And there's some similar statements in the same flavor by Hoybretz and Maury that I would like to share. It says that, again, if you're willing to assume hyperkiller SYZ, if you're able to deform hyperkiller manifolds to a Lagrangian one, then you can reduce a certain conjecture called Nagai's conjecture on degenerations of hyperkiller manifolds to a statement about the cohomology of these perverse sheaves. So you have to, the precise statement involves the Hodge structure of the cohomology of the perverse sheaves, and then it becomes a purely algebraic statement that you want to solve about the cohomology of certain perverse sheaves. So so this is the comment or remark. And then the thing we would like to focus on is how one can approach Pij equals Hij, or how one can better explain this phenomenon without any hyperkiller metric, whether there's an algebraic way to approach this phenomenon. So now we'd like to focus on this question, and we want to also to enhance it. Namely, we want to be able to lift this identity between certain numerical invariants to maybe some correspondence at the level of sheaves or categories. So this is the first goal. And the second goal is there's a compact setting that we're satisfied with numerical invariance, but we also want to see if there's a way to unify the compact setting and the non-compact. For example, we'd like to make a statement which makes sense for, say, Hitchin vibrations. So this is to unify compact and non-compact. And thirdly, and importantly, that we want it to be purely algebraic, or in other words, it's symplectic. So we don't want anything global, anything hyperkiller at all. This is the goal. And now the idea is to find a way not to match the numbers, but to match the actual sheaves. So if you think about it, we have 2n plus 1 interesting perverse sheaves, the P0 to P2n. These are the perverse sheaves. And we happen to have 2n plus 1 interesting coherent sheaves, which is the omegas, so the sheaf of differential forms. And of course, if you take the cohomologies, you get the dimensions of the cohomology groups, so you get the perverse numbers and the Hodge numbers. That's where we started. But now the question is whether there's a way to match these two. Of course, you can say that I want to match P0 with omega 0, P1 with omega 1, but is there a way to not to match them by hand, but to state a mathematical statement? So now the key idea, or the say the so conceptually we would like to match these two, and now we want to solve, first of all, the problem of making a coherent sheaf out of a perverse sheaf. So the perverse sheaf is kind of topological, and we want something coherent out of something topological. And the naive, you want something coherent out of topological. And the ideal solution is to consider a certain limit of a perverse sheaf in the sense of Saito's Hodge modules. So Saito's Hodge modules provides a way to make a coherent sheaf out of some topological information. And first of all, to do this, we have to enhance the perverse sheaves into Saito's Hodge modules. And the definition is quite involved, but I'll just say what the objects are. So the objects, Hodge module will be, say, a triple where n is a regular holonomic D module. So on my variety, or on my variety M. And this is a good filtration called the Hodge filtration. And K is my original perverse sheaf. So this is a perverse sheaf. And the Hodge module, first of all, it satisfies the D module, matches the perverse sheaf under the so-called Riemann-Hilbert correspondence. And then there are many, many conditions for such a triple to be a Hodge module. So there are lots and lots of conditions. What I want to say is that this Hodge module formalism, it allows us, first of all, to lift a topological object, the perverse sheaf, into something more coherent. And also it helps to remember, so that when we have a Lagrangian fibration, you do not only remember the topology of the fibers, but we also want to remember the variation of Hall structures when we do, say we have a generic abelian fibration and we want to remember all the variation of Hall structures. So the typical examples of Hodge modules will, first of all, if you have a trivial local system, I mean, you have the constant sheaf, and then the corresponding D module will just be O, and then this filtration is also trivial, concentrated in degree 0, and then this is the constant sheaf up to some shift. This is the constant sheaf. And this will be called the QM with a superscript H standing for Hodge. And this is the, say, the trivial Hodge module on my M. And also, if you have a polarized variation of Hodge structures, and then you can make it into a Hodge module by remembering the holomorphic bundle and also the Hodge filtration and also the underlying local system. So now comes the important part. So if you have a Hodge module, you can take a limit, and the limit is given by the associated graded piece with respect to the Hodge filtration. So this is the limit that I want. So you just take all the associated graded pieces and you put them together, and then this graded piece will be a graded piece of dm module. So the graded piece of dm will be just O of T star M, and you naturally get an O of T star module. So you can view it as in the cotangent bond of M. So this is a coherent sheaf on the cotangent bond of M, and this is the limit of the Hodge module. So you naturally get a coherent sheaf because you naturally have a Hodge filtration and everything, and you get a coherent sheaf on the cotangent bundle of M. And if you're wondering what the sheaf is, the support of this sheaf is the so-called characteristic variety of the D module. So by upgrading everything to Hodge module, you not only get say a cycle on the cotangent bundle, but you also get a real nice coherent sheaf. For example, if you take the trivial Hodge module, then the graded piece will just be the O of M, but this time you have to view it as the structure sheaf of, the structure sheaf of the zero section inside. So this is a zero section inside the cotangent bundle. Now, if you have a variation of Hodge structures, the graded piece is, say, a coherent sheaf on the cotangent bundle, but also in this case, this is the direct sum of all the graded pieces. Another way of viewing this is that this is naturally a Higgs bundle, because then you have the associated gradient of the Gauss-Manin connection, which gives you the Higgs field. So this is the Higgs field, and so you get a natural Higgs bundle on M, which is also a O T star M sheaf. So O T star M module. Now comes to some technical formulas to be able to formulate an enhanced or categorified version of the perverse Hodge symmetry. So I have to remember 3 formulas involving Hodge modules. So now let's take M and B for simplicity. Let's take M and B both non-singular, and the pi will be a projective map. And then the first formula is Seidl's decomposition theorem. It is a natural enhancement of the BBDG decomposition theorem at the level of Hodge modules. As I said, whenever you have a polarized Hodge module, say on M, and then you can take the push forward in the sense of Hodge module, and then there's the natural decomposition into a number of shifted Hodge modules inside the derived category. So in our case, I have this Lagrangian fibration from M to B, and then I just take the constant or the trivial Hodge module. So this is my trivial Hodge module, and then it will give me a decomposition of the push forward into 2m plus 1 Hodge modules. Again, the decomposition is not canonical, but these Hodge modules are canonical, and so I get 2m plus 1 Hodge modules, and they're triples that I'll call PI and the Hodge filtering F of PI, and also this original PI. This is my perverse sheaf. This is the perverse sheaf PI that I started with. So this is how we do the decomposition in the setting of Hodge modules. The second formula is called Lomon's formula. It tells you how to compute the gradient of the push forward of a Hodge module. So it basically tells you that pushing forward and taking graded pieces commute with each other. But the precise formula has to involve two maps. So you take, so there's this two arrows. But first of all, you take M cross T star of B over B. And then this map is the differential. This is the D of pi. So you just take any forms from B and you pull it back to M. So this is the differential map. And then the P2 is the second projection. The formula says that first, for example, you want to compute the push forward and then the graded. So the graded of the push forward. And by Seidel's decomposition theorem, you can rewrite it as the direct sum of the graded of some shifted Hodge modules. But then Lomon tells you that you can just follow this, the two maps. You go first this direction, then this direction. So first of all, you take the graded of n, you pull it back in the derived sense via the first arrow, and then you do some tensoring with the relative canonical sheaf to fix some issue with their duality, and then you push it forward again in the derived sense to T star of B. That's how you compute the graded of the push forward. So this is the second formula, and then the third is
so Lom's formula is for any M to B.
This is for any M to B, yes.
And in the case of Lagrangian fibration, so if you take this n special n, what do you get?
This is what I'll do. This is the mystery to us. So I'll explain that. So the third nice formula is it's basically the self-derived intersection of the zero sections. You have the zero section and you want to intersect with itself, then by intersection I mean the derived pullback via the zero section of the O of the zero section, and then the formula is given by, you can imagine all these tangent bundles. So I write it as the direct sum of omega I shifted by minus I, but I have to take the dual. It's actually all these tangents shifted by I. So with these three formulas in hand, now I can state the main conjecture that we came up with. So I write this diagram as, and part of it you've already seen it. This is in Lomon's formula, And then I continue with another arrow, which goes from M to M cross T star B over B. This is the 0 section again. And the composition is again the 0 section of M. So now I'll start observing things. So I start from this side, from T star of M. And this is where we start with Lomon's formula. And then here you take the graded of the trivial Hodge module, O of M. So this is here. And first of all, you do derive the pullback, and you end up in M cross B, M cross T star B over B. And then you fix it by tensoring with the relative canonical. And then you have two ways to go. You can either do P2 derived push forward to land in T star B. This is in Lomon's formula. And the other way to go is to pull back again via this map 0 of pi. So you have two ways to go. You either go this way or you pull back again. So now if you follow these formulas, first of all, Lomon tells you that if you do this push forward, you will end up with the direct sum of all the graded of PIs. So I should say curly PI. With some shift, minus I. So this is what Lomon tells you. And if you go the other way, you arrive at the derived self-intersection because you're basically just pulling back the 0 section via the 0 section. And then you arrive at the direct sum of, again, 2m plus 1 things, omega I of m shifted by minus I, and with some dual. And then you have to also do this compensation of the relative canonical. So now you see that if you go these two ways, each time you arrive at 2m plus 1 interesting things. Now what you know is that they're in two different things, two different places, but then you can make them meet by filling this diagram into a Cartesian diagram. So this is the projection. So this is the vibration pi, and this is again the 0 section of B. So now you have on M and on T star B, you both have 2m plus 1 interesting things. And then exactly those are the PIs and the omega I's, or things associated with them. And now the natural guess is that when you finally make them meet in B, then they will match term by term. So this is how we arrive at this conjecture. And this conjecture says that whenever you have a Lagrangian vibration, say B is non-singular, then on one hand, you follow Lomon and then pull it back to B via the 0 section. So this is the one hand. On the other hand, you take the omega I, and then you do the derived push forward. And then you have to do some dual, and they will match. Finally, in the derived category of coherent sheaves on B. And this is a matching, a term-wise matching. Of course, if you do all the direct sums, then you know by base change that the direct sums together will match with each other. But now I'm asking for a term-by-term matching. And this is...
So can you give one example, for example,
yeah.
case 3? Oh, yeah.
Yeah, I'll come with the example. So first of all, I'll make some remarks why this recovers the previous perverse Pij equals Hodge J. So if M is compact, so first of all, the conjecture makes sense without any compactness assumption. So But when you have a compact manifold M, you can apply Lomond to this. So I have to say that Lomond, for Lomond to work, you have to assume the map to be proper. So now the B to a point is proper, and then you can apply Lomond again. On the one hand, you arrive at this more perverse thing, and on the other hand, if you believe the conjecture, you arrive at the more Hodge thing. And if you see what pushing to a point means, and then eventually you will get this identity that we started with. So this is how you recover the Pij equals Hij via this conjecture. And also when I equals 0, so I take just the most trivial perverse sheaf and the most trivial coherent sheaf that I have. So when I equals 0, my P0 Hodge module would just be the trivial Hodge module. So the underlying V module will just be O, and the graded piece will be O again, but this time viewed as the structure sheaf of the 0 section. And my omega 0 is just the O again. So now if you believe the conjecture, then on one hand, you do pull back the 0 section via the 0 section. And on the other hand, you do the derived push forward of O, and you take the dual. Now, the derived intersection, the self-intersection formula tells you that you know how to compute the self-intersection. This is a bunch of omegas up to some shit. And now if you compare the two, you see that this conjecture specializes in the case of Lagrangian vibrations to, first of all, that the derived push forward of O splits into some shifted sheaves. And this is, of course, the famous theorem of Kollars. And secondly, it specializes to a nice result of Matsushita saying that each of the higher direct images of O is, so the Ri push forward of O is precisely omega I of B. So this is Matsushita's theorem. So it specializes to some important known results. And now, let's say, honestly, we only have this conjecture and we don't know much about how difficult it is. So we can do a bit of tests. For example, I can write this proposition that we did a number of tests. For example, that this conjecture holds for smooth Lagrangian vibrations. If you have a smooth map and a smooth abelian scheme where the source variety is symplectic, and also it holds for elliptic K3s or any elliptic vibration from a symplectic surface. And you can do a little bit more by taking the Hilbert schemes of your elliptic K3, mapping to the Hilbert schemes of the base curve. And this Lagrangian vibration also works. So I write it as 2 prime. So from the decomposition point of view, this 2 prime is not really easy because the decomposition theorem is quite complicated. But somehow the combinatorics are good enough for you to work it out. Now comes the examples. I want to show you somehow how true this conjecture is, or in which generality should the conjecture hold. For example, let's do a first toy example. I want to know if this conjecture holds in greater generality. But then I just take, say, the product of 2 curves, C cross B, mapping to the second curve B. This is a really simple setting. Now, if you believe this conjecture, now you want to test, for example, that on one hand, you do derived pullback of the graded of P0, On the other hand, you do the derived push forward of O of S. You want to see when they are the same. Then you do an easy calculation. This derived pullback is just a self intersection. This is O of B direct sum of omega B shifted by -1, taking the dual. On the other hand, you also get O of B, but now this is direct sum of O of B to the power of the genus of C shifted by -1, and then take the dual. But now you realize that for this conjecture to hold, even in this very simple setting, you have to force B and C to be both elliptic curves. And in particular, the product will be symplectic. So in this naive example, or you already see that somehow this phenomenon, this term-by-term matching, it has to involve certain symplectic geometry. Now, I'll also try to show you why this conjecture it holds for smooth Lagrangian fibration, and this really involves so this is doable, but also you can see why the symplectic form plays a role. So to begin with, we have the tangent sequence and the cotangent sequence. So there's the tangent and the cotangent sequence. And then the symplectic form, it builds a bridge between the tangent bond of M and the cotangent bond of M. And under this, so this isomorphism induced by the homomorphic symplectic form, you can identify the pullback of the tangent of B with the relative cotangent, and the relative tangent with the pullback to the cotangent. So this is how you do the matching. And the consequences will be that if you do push forward of the relative omega-1, you get the tangent of B, and you do the R1 push forward of O, you get the cotangent. You get omega-1 B. So now if you want to see whether this conjecture holds, or to get a feeling with this conjecture, for example, you want to calculate a non-trivial term in this conjecture, you take I equals 1. So on one hand, you have the graded piece of perverse 1. And this is just a variation of hot structure. It has nothing to do with hot modules or anything. It's just a variation of hot structures. And you want to calculate the derived pullback. On the other hand, you want to calculate the derived push forward of omega-1. Then you can do that. First of all, the derived push forward of omega-1, it follows from the cotangent sequence. So this is the second line here. So I did the calculation. In the middle, you have the derived push forward of omega-1. And then after taking the dual, one hand, you get an omega-1 B tensoring with a bunch of things that we've seen many times. And then on the other hand, you get T of B and again, tensoring with the direct sums of omega I with some shifts. On the other hand, you were interested in the derived pullback of the graded piece of P1. Then, as I mentioned before, this graded piece of P1, it naturally lives on the cotangent bond of M. But now it comes from a variation of hot structures, so you can also view it as a Higgs bundle, and it's a Higgs bundle on M, and it's a sheaf on T star of M, supported scheme theoretically. So it's supported as a set in the zero section, but the scheme theoretically it has some thickening. But then you can resolve it, meaning that you can write the graded piece as in a short exact sequence involving two trivial Higgs bundles, and viewed as a sheaf supported on the zero section. It scheme theoretically supports on the zero section. So you write this short exact sequence, and then you do the derived pullback, and then you arrive at precisely the same formula the left-hand side term and the right-hand side terms are the same. Now, if you're wondering whether the boundary maps are also the same, and you can check that the boundary maps are also the same, and because they're both induced by the Gauss-Manin connection. So for the Higgs bundle construction, it naturally uses the Gauss-Manin connection, and for the second, this is basically Katz-Oda's definition of the Gauss-Manin connection. So it's the same boundary map. So here, I'm just trying to show you why one should expect such a conjecture to hold. So now I have 5 more minutes. Let me say that there are some further refinements of what we did, the previous conjecture, but it involves more machinery and more terminology. So first of all, you can enhance this conjecture by taking care of the grading on T star of B. Then you can arrive at this conjecture, which uses the graded piece of the Duram complex, and it shows a symmetry between the 2 indices, I and K. So this seems complicated, but in simple words, it says that somehow if you're interested in all these Hodge pieces of perverse sheaves, then the kth Hodge piece of the ith perverse piece will equal the ith Hodge piece of the kth perverse piece. So there's a symmetry between I and K. In all the previous examples, we can also show this version of the conjecture. And then the second possible refinement is more conceptual. So now, so far, we're trying to relate the PIs with the omega i's by making them meet. And in the end, we decided to make them meet at the derived category of coherent sheaves on B, but they might meet even in a better place. So now, if you suppose for simplicity that my Lagrangian vibration has a section, then previously we were trying to compute the derived push forward of omega I. Then with this section, and also with the help of, say, the relative Fourier-Mukai transform. So this is an abelian vibration, and it's actually expected that there's a relative Fourier-Mukai transform. It's not known in general, but in some cases, one can construct such a relative Fourier-Mukai transform. Then the derived push forward is the same as doing this Fourier-Mukai transform and then pull back via the zero section. So this is how you rewrite the derived push forward. Then once you have this, then I can draw this big diagram. This is what we view this, how we view this problem. So on the left-hand side, we start with the perverse sheaf obtained from the decomposition theorem from this Lagrangian vibration M to B. So we have these perverse sheaves that we call PI. And the first thing we do is we enhance it into a Hodge module. This is the PIH, and then we're taking the graded pieces. This is the GER of PI. And then previously we did pull back via the zero section to arrive at B. And on the right-hand side, we start with my omega I. And then to compensate all the duals, I take the Fourier-Mukai inverse transform. So now I arrive at, again, the derived category coherent sheaves on M. And then I do the section pullback. So this is my R pi I r pi of omega I tau. So this is a previous story, but now we're still wondering if there's a way to connect. We don't want to push everything to B or pull or pushing or pull back. Maybe there's a way to relate these objects already at the level of T star B and M. And we have some evidence that some form of relation should be true, namely that if you look at things at the level of support, so not the coherent sheaves, but if you look at the support of the coherent sheaves, then this relation, this question mark here, should be just the deformation to the normal cone. So you start with the Fourier multiply of your omega I, and then you take the support of your sheaf, and then you do the deformation to the normal cone, and then you should arrive at the right characteristic variety of your PI. So this is what we believe should be true. So now here, where the symplectic form plays a role is that when you do the deformation to the normal cone, since B, the other section inside the M, so B inside M is a Lagrangian, then its normal bundle is the same as the cotangent bundle of B. So the normal cone here is just the cotangent bundle of B. And then you can see in some basic, for example, surface to curve examples to see how this deformation to the normal cone works. And we're now currently trying to somehow to formulate a mathematical statement involving this question mark, maybe at the moment only for, say, Hitchin vibration or for the Bouvier-Mukai system. And this is the picture that I want to share. And I think that's it. Thank you.
Yes, thank you. So, are there any questions or comments? So I'm wondering for your comment.
Hi, how are you? Yeah, it's a very nice talk. Yeah. So, what does the PI capture all the Chern classes of M?
All the Chern classes of M.
All the higher Chern classes, yeah, as an algebraic cycle, let's say.
Yeah, I think so our proposal is that the PIs should calculate the derived push forward of all the omega i's to B.
Yeah, so that would give you all the Chern classes.
That should give you yeah. But it's still complicated to calculate any of the PIs. Yeah, but the idea is that they should give the same information. That's the point.
Okay.
Yeah.
More question? So I'm wondering for your conjecture, what can you deduce from your conjecture? For example, can you recover what you have shown before?
Yeah. So this is the remark. So the conjecture implies what we had before, and also it specializes to Matsushita's result.
Oh.
Yes. So this conjecture really is a, say, categorical.
Your conjecture, you assume B is smooth.
Yes. One can also state a version without B smooth. That also specializes to what we had before. So here I'm just simplifying things.
So you can think about this as a Havicada analog of what's the mirror of the tangent bundle or cotangent bundle of M in the
Yes. Yeah. Yes. Yeah. You see appear in the Fourier Mukai transform and all that. It has some, yeah. It has some flavor of that. Yeah. But so yeah, this proposal is to relate one complicated thing to another complicated thing. So yeah, the PIs are not necessarily easier.
If no more questions, so let's thank Yin Qizhen again. So for his nice talk. Okay. Okay, so see you in 2 weeks.